So the problem I gave you to get started with was to take the figure 8, and here I've drawn it as though I've taken a picture of a figure 8 which is oriented. But what I'm asking you to do is to figure out what are the elements in the fundamental K of this figure 8. Now, not the fundamental quandle, but the fundamental K. What's the difference? Can you remind me? So the difference between quandle and K is that Ks relate to unoriented knot diagrams. In other words, our K operation needs to be something that doesn't see the difference, for example, at a crossing between the inbound arc and the outbound arc. That if we forget about orientation, those two have to be equivalent one to another. And so a K is a particular type of quandle, right? A quandle will see the orientation. If we forget the orientation, we still have a quandle, but now it has a different structure, usually a simpler structure, and we call it a K. So the first step, I guess, for this diagram is we should erase those little arrows and pretend that we have an unoriented version of the figure 8. So with our unoriented figure 8, now our job is going to be to take our arcs, and this diagram is already helpfully labeled the 4 arcs for us, so we'll just go with those as our labels. So this is x1, x2, x3, x4. Those are the 4 arcs in this diagram. And each one of those arcs has got to be one of the elements that makes up the fundamental K. So I'm just going to think about building an operation table for the fundamental K, where the first 4 elements that I'm going to put in my operation table are those 4 arcs. x1, x2, x3, x4. And our K operation will denote with this little triangle. So we know what belongs on the diagonal of this table. How do we know that? For example, what's x1 triangle x1 have to be? X1. That is one of the 3 fundamental properties that characterize any quandle operation that comes from invariance under the type 1 Reidemeister move, the twist. Right? That if I ever have an arc that intersects itself, then whatever happens at that crossing is the same arc is meeting itself 3 times. Basically, x1 triangle x1 is x1. x2 triangle x2, likewise. x3 triangle x3, likewise. x4 triangle x4, likewise. Okay, so the diagonal is straightforward. What else can we fill in? So there's our mnemonic for this K, is that A under B becomes C. So for example, x3 under x1 right here becomes x4. So I'm just going to write that out here for a second. x3 under x1 becomes x4. That's what's happening at the crossing that I'm now going to label crossing A over here, just so we have a way to refer to it. Right? But again, because of the unoriented nature of a K, there needs to be a symmetry with respect to an interchange of the 2 under arcs, because x3 going under x1 and becoming x4 is the same as x4 going under x1 and becoming x3. x4 triangle x1 equals x3. So let me ask this quick question. So now we have 2 more entries that we can fill in this operation table. But what is the algebraic connection? How could I get from this equation to that equation? What operation am I doing there? The relationship between these 2 equations is what I'm doing to the first one is I'm triangling on the right by x1 on both sides. If I do that, then I get x4 triangle x1 on the one hand, and I get x3 triangle x1 on the left-hand side. But how do we simplify that? What did we agree about the K operation for this very reason? Self-invertible. It undoes itself. So triangling with x1 twice is the same as not triangling at all. Right? So that's the one property that makes the K operation more specific, a more specific case of the quandle operation. Quandle operations are just required to be invertible. K operations have to be their own inverses. Right? So not only are they invertible, they're invertible by their own selves. Right? So triangling with x1 twice makes it disappear because we need that symmetry that comes from forgetting our orientation. Right? So now we can fill in 2 more entries. x3 triangle x1 is x4, and x4 triangle x1 is x3.
And then x2 triangle x1 and then x2 triangle x1 are the ones that we have to create an extra.
x2 triangle x1, so 2 going under 1, that appears never to happen. Right? So 2 going under 1, that's a new element. Right? So probably what you want to do is exhaust all 4 of your crossings first to fill in as much as you can of the table without adding new elements.
I did
then
x4 triangle x2 gave me x1.
x4 under x2 becomes x1. Yes, I see that happening at this crossing right here. 4 under 2 becomes 1. So let's color that purple maybe. 4 under 2 is 1. And that also means what else is true? This is crossing B. If we go the opposite direction along that crossing.
So then x1 triangle x2 equals x4.
Yes, 1 under 2 becomes 4, and that fills in that entry. We got 2 more crossings that we can mine for information. Let's go to this one on the bottom. What's happening at crossing C?
x3 triangle x4 equals x2.
3 under 4 becomes 2, yes. So that goes here. And what else?
And then now x2 triangle x4 is x3.
2 under 4 becomes 3. Great. So we have 3 out of 4 entries in that 4th column. If we go to the last remaining crossing, what's happening there?
x1 triangle x3 equals x2.
Okay, 1 under 3 becomes 2, and therefore also
x2 triangle x3 equals x1.
2 under 3 becomes 1. Great. And so once we've gotten all 4 of those crossings accounted for, we still have blank spots in our operation table. And that's kind of a clue, right? That we don't have enough stuff in our fundamental K to completely tell us, to completely determine all the operation table. And as you observed a minute ago, that's because, for example, x2 triangle x1 is not simplifiable based on the crossings in this diagram, because x2 never crosses under x1. And so that, therefore, has to be a new element. So we throw that new element into the mix. And if I throw it into the middle of the table right there, that means that now I have to add it here. x2 triangle x1. And it now makes our operation table bigger than it was before. So now we have even more to do. But we're going to hope, clear out some space here. Once we've added in the 4 elements that complete our 4x4 block for my original 4 arcs in my diagram, in my fundamental K, we end up with these 4 new things. And so we certainly are now going to have at least 8 elements in our fundamental K. And the question is, how do we fill in some of these entries that are still missing? So let's take this one that we were looking at a moment ago. x2 triangle x1, triangled with x1. And John, your observation is right on, because what we need, because we don't have associativity for quandle operations, what we need for this is we need to distribute. Okay? We need to distribute this triangle x1 into the parentheses, and according to quandle properties, what happens when I do that distribution?
x2 triangle x1.
x2
triangle x1, triangle x1.
Yes, right. It distributes over itself and becomes x2 triangle x1, triangle x1 triangle x1. But then,
sorry.
No, go ahead.
The x1 triangle x1 is just x1.
x1 triangle x1 is just x1. x2 triangle x1 is just x2 triangle x1. Huh. That seems unfortunate, because we just end up exactly right back where we started. So this particular distributive property doesn't seem to have helped us. Let's see if maybe some of the other distributions might be able to be simplified. So some of these we should be able to do completely, like this entry. If I do this distribution, I'm going to get x2 triangle x2, parentheses, triangle, x1 triangle x2, parentheses. But x2 triangle x2 is, and x1 triangle x2 is x4, and x2 triangle x4 is x3. So that one we can do. That was the second entry in this row. There, x3. And so, so you can see that some of these we can apply the quantile operations and get back to the original simplified version. I think the same is probably also true for the next entry in this row, because if x3 comes across, we'll get x2 triangle x3, triangle x1 triangle x3, the former of which is x1, and the latter of which is x1 triangle x3, x2. So we end up with x1 triangle x2, so I think this is x4. So we can make a good amount of progress trying to simplify some of these, but there do seem to be some that are going to remain resistant to what we're trying to do. The next one's going to be an issue because one of the distribution factors is going to be x1 triangle x4, and that's one of the elements that we don't have a way to simplify. So I think maybe the thing to do for now is fill in as many entries as you can that are in this 8x8 table, and then maybe we can look at some other ways of simplifying the things that are left over. But for now, yeah, we may not be able to fill in all 64 of these just yet. Even if we could, that's a ton of busy work. So get the ones you can for now. Take a crack. I would recommend taking a crack at one of the ones that's down in this block. These are going to be really fun because you're distributing one of these and one of these across one another. So find at least one or two of those that simplify as well.
So would you like FOIL?
Well, FOIL, that's a good question, right? Because, let's think about that for a second. So let's pick on an example.
I was working on x2 triangle x1.
This one.
Triangle x3, triangle x2.
Okay. So yeah, if we do that one step at a time. So FOIL should be okay as long as we pay attention to parentheses and we pay attention to order, right? So if we do the one that Brittany, you're talking about, what would that look like?
x2 triangle x3 together.
Mm-hmm.
Triangle x2 triangle x2.
x2
parentheses.
triangle x3, triangle x2 triangle x4. Wait, sorry, what did you say?
Triangle x2 triangle x2.
x2 triangle x2?
Yeah.
So there's the result of foiling this. And reassuringly, when we look through this list, every one of these is simplifiable in our table, right? x2 triangle x3. Well, okay, but then the other issue is where do we put, there should be a larger set of parentheses around some of these, right? So what's the next level up grouping? What are we potentially losing here? So let's do the FOIL, let's expand out the FOIL, right? When you're first teaching FOIL, usually you do it as a twice iterated distributive property, right? So let's do that just to make sure that we're being careful with where all the parentheses go. So if I first distribute x3 triangle x2 across the triangle on the left, then I'm going to end up with x2 triangle x3 triangle x2 triangle, and I'm going to put parentheses around that first thing, right? x1 triangle x3 triangle x2 But now the question is, do we have a left distributive property in quantile operations? Assuming for the moment that we have left distribution, then these would each go here and here, there and there. And we would get exactly what Brittany proposes that we get, just with an extra set of parentheses here and there. And each one of these four things has a way to simplify it from our operation table. x2 triangle x3 is x1. x2 triangle x2 is x2. x1 triangle x3 is x2. x1 triangle x2 is x4. Okay, and the fates are still smiling upon us because x1 triangle x2 can be simplified to x4. x2 triangle x4 can be simplified to x3. So what we really have is x4 triangle x3, which isn't simplifiable, but it's one of our 8 elements. So we would just write it, x4 triangle x3. Okay. So that's not so bad. As long as we can convince ourselves that left distributivity is a thing. So the right distributivity was a reflection of the type 3 Reidemeister move, right? And the fact that the color that we get, quote unquote, for this top strand, if the bottom strand is colored X and the other crossing strands are Y and Z, has to be the same both before the type 3 move, in which case we get X triangle Y parentheses triangle Z, and then also afterwards, where now we're on the right-hand side, and now we have X triangle Z crossing under Y triangle Z. So what we need to do then, if we want to convince ourselves that left distributivity is also possible, is we need to come up with a way of getting X triangle the quantity Y triangle Z up here at the top. Right? So Y triangle Z happens to be this strand over here out on the right. And so we need to somehow have a way for X to cross under that, right? And then to be able to move that to the other side of the crossing here, type 3 Reidemeister move, and see what happens. Let's see if we can talk ourselves into that. So how are we going to get X triangle Y triangle Z with the Y triangle Z in parentheses? So working backwards, if we have a picture like this, where I have a Z strand, which is the overcrossing, and a Y, which is the under, then on this side that becomes Y triangle Z. And if I have my third strand that crosses under both of those, and the middle of those arcs is called X, then this arc on top is going to be X triangle Y triangle Z in the order that we want. And so let's apply the type 3 Reidemeister move to this and just see what happens. So if we slide that strand from the left side of the crossing to the right side of the crossing, while retaining the labels of the Y and Z arcs, so those still have to be the same that they were before. So this arc is still Z, this arc is still Y.
Is the one in the upper left still Y triangle Z?
And the one in the upper left is still Y triangle Z. But there's no Y triangle Z in this expression, which is kind of reassuring because now this arc is no longer crossing Y triangle Z. Instead, it's crossing Y, and then the result is crossing Z. The issue, I suppose, is what do we call, if this strand in the middle is still colored X, okay, then on the one hand, this is just X triangle Z. Whoops. And then this one over here is X triangle Y. And X triangle Y is not actually crossing under X triangle Z. So something's feeling weird here.
I have a question about the first picture.
Yeah. So before we give up on the left distributive property, let's remember that we know some examples of concrete operations that satisfy Quandl and Key axioms. So let's try with X triangle Y equals 2Y minus X. Right, over the integers. X and Y integers. So this operation satisfies the properties of a K operation, the K axioms. This was the operation that we used to color integer color rational tangles. Right, So this is something that will be weigh heavily on our minds as we're preparing our workshop for May 7th. So if I try that, let's just pick some numbers. 3 triangle, 2 triangle 4. I don't know, just as an example. And let's compute that out. So on the one hand, what's 2 triangle 4 going to be? Twice this minus that. 6. 2 plus 6 is 8 times. Yep, And then 3 triangle 6, twice 6 minus 3 is going to be 9. Now let's try the distributive property and see if it works. 3 triangle 4, the left distributive property. Because if we're chasing a wrong conclusion, hopefully we'll see that reflected here. So when we do this with 3, 2, and 4, it seems like it does work. But you're thinking that might have been a lucky accident. So I don't know, maybe let's try it with some bigger, weirder numbers. -2, triangle 8, triangle 13. Just for kicks. Try and push the envelope a little bit. We've done a couple examples and we haven't found that it doesn't work. So we could try to prove that this is true in general for this concrete realization of the k-axioms, right? So what is x triangle y triangle z going to be? And then what is x triangle y triangle z going to be? So this particular kind of k operation is left and right distributive. So that's interesting. But hold on, let me backpedal on this for a second, because I don't actually know for sure that does this satisfy the k-axioms? So we know it satisfies the quandle axioms, because that's the context that we met this in the first place. So we know, for instance, that x triangle x is equal to x, and that the self-distributivity property holds, right? X triangle y triangle z equals x triangle z, triangle y triangle z. I think I wrote that right this time. But do we know, for the k-axioms, that x triangle y is equal to x? Right, that's the thing that separates k-axioms from quandle axioms. Not only are they invertible, but they're self-invertible. Let's just test that real quick, because now...
Using the x triangle y?
Yeah, using this definition of this operation. So that would be 2y minus x, triangle y, which is 2y minus quantity 2y minus x.
Mm-hmm. Yep.
Huh.
Maybe x.
How about that? And just because I want to be thorough, x triangle y triangle z is going to be 2y minus x triangle z. That's going to be 2z minus 2y plus x, right? And on the other hand, x triangle z triangle y triangle z. Oh yeah, x triangle z triangle y triangle z. That's going to be 2z minus x triangle 2z minus y. Yeah. And then that's going to be twice 2z minus y minus 2z minus x. Right? And that's 4z minus 2y minus 2z plus x. That's 2z minus 2y plus x. Yeah, so all those things are true. This is a k operation, and it is both right and left distributive. Whether all k operations are is another question. So let's just check it for this group operation that we also have been working on, right? x and y elements of a group G. So we decided this was a quandle operation. Is it a K operation? Let's check that real quick. We know that x triangle x is equal to x. We know that it's left distributive. These are things that we checked when we first met the definition of quandle. It's triangle Z, triangle Y, triangle Z. But let's check the left distribution. X triangle, parentheses, Y triangle Z. This is going to be Y triangle Z inverse times X times Y triangle Z. Y triangle Z is Z inverse YZ. Inverse X, Z inverse YZ. And the group operation is associative, so we can remove parentheses as soon as we take this inverse, and this inverse ends up being the product of the inverses in the opposite order. So we take the inverse of this rightmost factor, which is Z inverse, times the inverse of the middle factor, Y inverse, times the inverse of the leftmost factor, which is Z. X, Z inverse, Y, Z. And I don't think we can simplify that any further. So it's just going to have to be how it is. And then we just need to check X triangle Y, triangle X triangle Z. And that's going to be X triangle Z inverse times X triangle Y times X triangle Z. And there we'll drop in those definitions. Z inverse X Z inverse Y inverse X Y times Z inverse X Z.
So when you do the inverse, it's opposite order.
Yes, the inverse of a product is the product of the inverses in the opposite order. So that's going to give me Z inverse X inverse Z, Y inverse X Y, Z inverse X Z. And I think I have something different.
Yeah.
I don't think one of those simplifies into the other, or if it does, I don't see an obvious way to do that. So it might be that, oh, did we check that this was a K operation? X triangle Y triangle Y. That's Y inverse XY, triangle Y. That's Y inverse times Y inverse XY times Y. Uh-oh. It's Y to the minus 2 X Y squared, not equal to X. So unlike the previous example, this example was not only a quandle operation, but more specifically was a K operation, and it was both left and right distributive. This concrete realization of a quandle, while being a quandle operation, you show that it was invertible, but it's not self-invertible. And so what that suggests to us is that this group operation is not a good way of realizing the fundamental K of a knot, for example. But it is a good way to realize the fundamental quandle of a knot. Okay. So this is good at representing the big giant object, the big giant invariant, the fundamental quandle. Whereas this might be a more appropriate way of trying to get at the fundamental K. And I think this gives us some reassurance. We would still have to do some work, I suppose, to do the more general case of proving that K operations are both left and right distributive one with another. But I think for today, and for the sake of moving on, let's leave this as a conjecture. Conjecture is that K operations are left distributive. In other words, X triangle, Y triangle Z. If that's true, then we have a lot more ability to simplify elements in that in the operation table for the figure 8's fundamental K. If it's not, then we could really be stuck in getting a lot more elements than we know what to do with.